Hello everyone, welcome to yet another session for nanoelectronics. In the previous 5 sessions, what we have discussed is the electronic devices based on various nanostructures. And from today onwards, we shall see various optical devices which are related to nanostructures. So when we say optical devices, basically we are going to see the light amplification by stimulated emission of radiation, nothing but the lasers. The different types of lasers which can be manufactured using the recent nanostructures. That's what we shall be discussing in this session and few coming sessions. So let's get started. So before we start with any typical type of a laser, let's understand the basic principle behind the operation of a laser. Emission. So lasers are nothing but devices which emit light, and we are familiar with the operation of laser. We have seen laser, we have used lasers. So what we could see in the output of a laser system is a very focused beam of light. We may get different colors, right? We have seen the red color lasers, green color lasers. So we have different colors for lasers. So what is the basic principle behind lasers? And that principle is stimulated emission. Now consider that you have two energy levels. I shall show you a diagram here. So suppose you have two levels, E1 and E2, and such a way that the energy level of E2 is higher than that of E1. Now, these electrons in this energy level E1, they can jump to the excited energy level or to a higher energy level E2 if they absorb enough energy. What is that enough energy? Suppose this energy level is say 10 and this energy level is 30. So if they want to transit from this energy level E1 to this energy level E2, they must gain an energy of 30 minus 10 or E2 minus E1. So electron in their basic or ground state E1 can get excited to the higher energy level E2 if they absorb an energy of E2 minus E1. Now see, once they reach here, they cannot forever remain in this higher energy state. Now what do? They start emitting. So what happens are, the electrons in our excited state E2 can jump, or they can make a transition to the ground state E1 without any external force, given the condition, right? So what happens is, this electron in E2 can make a transition to E1 with an energy that is proportional to the population of electrons in N2, right? So for that kind of emission, we have not required any other kind of external force, and that kind of an emission is called spontaneous emission, right? So what has happened, electron from E1 has acquired an energy E2 minus E1 and has got excited to E2. From there, the electron can make a transition from E2 to E1, by which they generate an energy which is proportional to the number of electrons in our energy level E2. This is without the influence of any kind of external force, and such emissions you call it spontaneous emission. Now these electrons in E2 can also drop to E1 if they are activated or stimulated by some kind of an energy, this stimulating field. So in the presence of this stimulating field, if the electrons in a higher energy level gets transited to a lower energy level E1, then that kind of simulation or emission is called stimulated emission. It is stimulated by an external energy supply. Spontaneous emission, it happens spontaneously without the influence of an additional force, external force. So when it comes to light absorption, emission, the things that happening is absorption and emission. And emission may be spontaneous or stimulated. Stimulated means in the presence of a stimulating field or an external field. That's it. So now what are the conditions for if you want absorption to happen or simulation to happen? So see, if you want emission to dominate the absorption you have, then you must ensure that the number of electrons in our electric field N2 must be greater than N1. If you want your emission to be greater than the amount of absorption, which means you want more electrons to come from E2 to E1, emission to be large than absorption, then you must ensure that the number of electrons in E2, energy level E2, must be greater than number of electrons in E1. And this condition is called as population inversion. Because normally, see, electrons tend to remain in their ground state, right? So we are expecting a number of electrons in the ground state. But if you want emission to be dominant, what we have proposed is that we want more number of electrons in the excited state than in the ground state. So this is the basic concept behind lasers. Now we have different types of lasers, and that's what we are going to discuss. So conventionally we have the very normal PN junction lasers or the homojunction lasers. Now see, the homojunction lasers or the normal PN junction lasers, they have just one component, right? Maybe it may be a gallium arsenide type of lasers. So what happens is, in these kind of lasers, they have certain issues. One is that see, the region in this homojunction lasers or the active region which emit light in the homojunction lasers are not well defined. Their size is not well defined, their performance is not well defined. We'll see that in a schematic manner, we'll see that. Another thing is that for these homojunction or basic PN junction lasers, their threshold current is very large. Now what is the issue if you have a very large threshold current? You will have to supply a huge amount of current to generate a laser action, which is not desirable, right? So if you want a laser action, I'm in fact expecting a very spontaneous response of this laser. I'm activating my laser in very less amount of current. I need a laser action to happen, right? So in the normal PN junction diodes, they have a large value for threshold current, which means we'll have to supply a huge amount of current to get a proper laser action. So it was due to these reasons that scientists started thinking about other alternatives for these lasers. And of course, what we have today is the heterostructure semiconductor lasers. So what is a heterostructure semiconductor laser? Right from the name heterostructure, we can at least guess that we are using different types of materials, right? And the very common heterostructure junction that we are familiar with is, of course, the aluminum gallium arsenide and gallium arsenide region. So maybe we'll be using that. Let's see. We have a schematic of a homojunction or the commonly used PN junction laser as well as the heterojunction laser. What are the things that you can observe over here? Or at least whom do you find better? See, in a homojunction laser, we can see that in the first figure, in the first section, we can see the semiconductor regions which forms the laser structure. So we have the P-type gallium arsenide and the N-type gallium arsenide, and at their junction there is the active region and light emission. And this figure, this shows the energy level of or the band diagram of a homojunction laser. We can see the potential well in this figure, and finally we can see the distribution of active region and the corresponding light intensity. Now just see which one will be better. Definitely we can see that in this heterostructure semiconductor laser, the emission occurs only within a very thin active region. See, this is your active region which is made of gallium arsenide. And why is this a heterojunction? We have a aluminum gallium arsenide region, gallium arsenide, and further aluminum gallium arsenide. We have used different type of materials to synthesize the laser, and this gallium arsenide region, which is sandwiched between different types of aluminum gallium arsenide region, they act as a active region. And these layers, they act as the cladding layers. And we know that aluminum gallium arsenide, they have a larger band gap compared to gallium arsenide. And correspondingly, we can observe that, see, our light emission, it is very much confined just to this active region. What about this region? There is a huge spread in this light emission. Your active region is just this junction, right? But there is a spread in the light intensity, which means we may not get a much focused beam of light compared to this structure. Now coming back to this cladding layers. See, these cladding layers are they play a very important role in this confinement, because these cladding layers, they provide a kind of an energy barrier, and this energy barrier, they will confine the carriers within the active region, because of which our light intensity is confined in the active region only. Why is it so? In a double heterostructure or a heterostructure semiconductor laser, I have placed a lower band gap material between materials of larger band gap. That's what has happened here. So these two regions around our active region, these two regions, this one and this one, they are called the cladding layers, and they ensure that they provide a energy barrier to confine your carriers, your electrons within this active region. See, the cladding layer gives two functions. They inject the charge carriers, as well as they make sure that there is proper light confinement. Now, when a bias voltage, when a stimulating field is applied, these electrons and holes are injected to this active region. And since the band gap of our cladding layers is greater than that of the active layer, these injected electrons and holes, they are prevented from diffusing across our junction. So I am applying an electric field and injecting electrons and holes just to this active region, and literally they get trapped because of the higher band gap in these regions, in the cladding layers, because of which our charge carriers cannot diffuse through these junctions and cause spreading, which is the reason for your high intensity or directed light intensity. Now these electrons and holes, they create the condition of population inversion, which is a necessary condition for what? For your emission to dominate absorption. So since your population inversion has been created, there will be high amount of light emission. Is this clear so far? Okay. So now what happens is that, So what happens is that normally their operation range, the wavelength is about 750 to 880 nanometers. And see, when any of their parameters are fixed, you can vary your wavelength in several nanometers range. It may be the size of the active region, the composition of the active region and cladding layers, or the presence of dopants. If you can change any of these parameters, you can change your wavelength also accordingly. So the parameters which are responsible for getting a particular wavelength is the effect of dopants, the size of the active region, the composition of the active region, the composition of the cladding layers. So these all determine the wavelength of light that we get. And again, we make sure that the refractive index of our active region must be slightly larger than that of the cladding layers, and this helps us to confine the light. And so we are finding possibilities of confining our light. One that we found is the cladding layers have larger band gap, because of which electrons and holes in the active region gets trapped, they cannot diffuse. So population inversion happens and high emission. Another thing that we ensure is that the active region, they have a higher refractive index, which again helps to confine the light. So again, these heterojunctions, see what has they formed? They have formed a quantum well also. And in fact, this increases our carrier concentration and the amount of population inversion. This quantum well creation, it helps us to increase the carrier concentration and the amount of, and thus the amount of population inversion, which is obvious, right? So basically in optical field, the refractive index of the material is it's a dimensionless property or number, and this refractive index, they describe how fast the light can propagate through the material. And we have taken that the refractive index of the active region must be higher, right? So in case of gallium arsenide, aluminum gallium arsenide double heterostructure laser, the huge value of refractive index of gallium arsenide, which is nearly 5%, even larger than aluminum gallium arsenide, this gives a very good amount of optical confinement or confinement of your light. and this optical confinement factor indicates what fraction of the photon density is located with the active laser region, and this must approach unity. So this optical confinement factor is just an indicator of how well the photon density or the light density is located within your active region, and this must approach unity. When it approaches unity, it means you have excellent light confinement. Okay, these are the things that we have discussed so far. So there is simulation only within the active region. The cladding layers must provide energy barrier to confine our carriers, and when you apply a bias voltage, our carriers are injected into the active region, and because of the band gap difference, these electrons and holes, they remain trapped into our region. And other points, the wavelength things, the refractive index, you may just go through these points, that's it. Yeah. So we'll see a commonly used kind of configuration for double heterostructure lasers, and in this configuration what we can see is that the active region has a horizontal dimension, and because of which you can greatly reduce your threshold current. If you remember, larger threshold current was a disadvantage of a homo junction, because of which we thought of alternatives, and that's how we reached into heterostructure lasers, right? So because of the horizontal dimension of our active region, you can quickly reduce the threshold current. So since the structure is also like this, because of the horizontal structure of this active region, we can use this kind of a configuration of DH lasers in order to couple through fibers or waveguides or etc. So see the composition. We have the aluminum gallium arsenide region, gallium arsenide, further aluminum gallium arsenide region, and it is this gallium arsenide region, see here, which acts as the active region, and from which we get laser emission. So this is a horizontal active region, just the same thing that we have discussed, except that our layers are horizontal. So that's about heterostructure semiconductor lasers. So in fact, these heterostructure conductor laser, they have a active region of thickness in few micrometer range, that is say 0.1 to 0.2 micrometers thickness. But see, if we have anything of a larger dimension, our next intention will be to reduce that thickness, right? So the researchers started thinking, how can we reduce this 0.1, 0.2 thickness of these heterostructure semiconductor lasers? And that's how they reached it at quantum well kind of semiconductor lasers. So the purpose behind quantum well semiconductor laser was to reduce the active region or to produce very thin active region. So these quantum well lasers, they have excellent light confinement features, and just in the case of quantum wells who has discrete energy levels, they also provide light intensities of discrete energy levels, and those similar to the since it's a quantum well, it's a 2D structure, and their DOS will be that of a 2D structure. And the light emitted by these quantum well lasers, they do have various parameters, just as in the case of heterostructure lasers, which is the thickness of the active region. So by these factors we can make our quantum lasers much better in operation, which means they have excellent light confinement. So the shorter wavelengths can be obtained from our quantum well lasers than from our normal homojunction or heterojunction lasers, and our efficiency of our quantum well laser is also much greater than your conventional lasers. Because of this, the stepwise DOS function that we have for two-dimensional structures. So these all aid the light confinement in quantum well kind of lasers. So we can see two commonly used kind of quantum well lasers, the common structures that we use for quantum well lasers. Right. So structure 1, 2 and 3. We will discuss each one in detail. See, these two structures, let's not focus on this one right now. These two structures, we obtain them by changing the value of mole fraction. A common compound is aluminum gallium arsenide, right? So suppose your compound is aluminum, gallium, arsenide. Aluminum gallium arsenide of the type AlXGa1-X and aluminum arsenide. So we have their mole fraction as X, right? Now see, while changing the value of X, you can obtain these two functions. By changing the value of X, you can obtain these structures. How? See, you can change this value of X between 0 and to say 0.3. So when it is 0, this structure is gallium arsenide, and when it is 0.3, it becomes Al 0.3, Ga 0.7 arsenide, right? So as you vary the value of X from 0 to 0.3, the band gap also increases from 1.41 to 2.0 electron volt, forming us the compounds gallium arsenide to different composition of aluminum gallium arsenide. So in this structure, we have fixed the value of aluminum gallium arsenide. Suppose it is say 0.2. So it is Al 0.2, Ga 0.8 arsenide and gallium arsenide region. That's it. So in this structure, we can see that the quantum well has a width of say 5 to 10 nanometers, and this is immersed or put into a wider cavity of width W. So a quantum well is D, it is put into a well of wider width W, and this in fact enhances the light confinement, and they can thus separate the carrier and optical confinement properties. So in the first commonly used structure, what I have done is I have placed the quantum well of width, very small width, say 5 to 10 nanometers, into a wider cavity or a wider structure of width W, and this is optimized to enhance their light confinement, and this structure will have separate carrier confinement and optical confinement. They have separate way to confine your charge carriers, which is your electrons and holes, and they have separate optical confinement features. See, carrier confinement and light confinement structures. That's about it. So here we have a fixed value for gallium arsenide or aluminum gallium arsenide. We have placed the quantum well into a wider cavity which provides us better light confinement. They have separate light confinement, carrier confinement and light confinement structures. A similar structure we can see here. Now we can see that as in the case of this structure which has a fixed value of aluminum gallium arsenide, that's not happening here, which means this structure, they have a graded refractive index, which means their value is continuously changing. Here it was constant, right? Here this is continuously changing, and this we call the graded index the graded index separate confinement heterostructures. These, the graded index separate confinement heterostructures. So these are similar structures. We have seen this. So the difference in this structure, the second structure, is that they have continuously changing refractive index. And the third structure, what might this be? Just can you have a guess? You have seen the structure. These are the multiple quantum well implementation of our previous structure. Right. So an advantage of this quantum well semiconductor laser is that they require only a few number of electrons and holes to reach their threshold value than our normal homojunction or heterojunction lasers. Why is it so? Because in quantum wells, in the case of quantum wells, an addition of even one electron has a huge impact on their electrical, optical properties. We have seen that, right? In Coulomb blockade effect, SEDs. Yeah. So even one electron has a huge impact, because of which these quantum well lasers, they require only few electrons and holes to reach the threshold than normal kind of lasers. And just like heterostructure lasers, these devices, the quantum well lasers, also have extremely low threshold current. We have seen the multiple quantum well lasers, and here as we have seen in the previous figure, what we have done is we have combined a number of identical quantum wells, and this helps to compensate your reduction in the active layer thickness. So normally for quantum well lasers, your active region is very thick, right? That was the first thing which led to the innovation of quantum well lasers. So in case this reduction in active layer thickness is going to pose any problems for us, the multiple quantum well structure of lasers helps to compensate for that reduction. Right. So as we have seen here, our previous structures are found by grading the composition of aluminum gallium arsenide from 0 to 0.3. And in the other case, we have a grading refractive index, hence their name, graded index separate confinement heterostructures. Right. Now let's see the relationship between gain and current density. So we can see that for a single quantum well here, there is an exponential increase in gain with an increase in current density. And in the case of multiple quantum well structures, with NW. N suffix W is the number of quantum wells. So as you increase the number of quantum wells, we are getting highly focused gain. See, when it is 4, we are getting a quick increase in the overall gain compared to when it is a single quantum well. So we can relate a laser, a device gain to the current density, the injection current density. And we can see that there is an exponential relationship between our current density and gain. And another thing that you can observe is that for multiple quantum wells, as the number of quantum wells increases, there is a quick increase in your overall gain. That's it. Yeah. So in this session, we have discussed about lasers, two kinds of lasers, heterostructure and the quantum well semiconductor lasers. We have seen what is the difference between them with respect to the conventional ones, their operation, their common structures. So that's what we have discussed in this session. Please go through it and let me know if you have any doubts. Thank you.